Hey guys, welcome to day 7 of college algebra. We're going to be talking about radicals and how to simplify radicals. If you have certain calculators, this can do a lot of today's homework for you. The Casios are famous for this. They will simplify all the math for you. TIs don't, at least in general. Some do, most don't. Our goal today is to practice kind of the radical properties. And then on Monday, we're going to talk about, how to actually take those radical properties and apply them with variables. Because the same properties that work today will work on Monday. It's just with variables involved, it can be rather tricky to put those two things together. And so that's what we're going to do. For today's assignment, we're looking at close to 20 problems. That's a lot. I may accept late homework on this one because I know you only have one day to work on it. So please take your time. Like I said, there's a lot of resources out there to help you with this. Our goal is this is just to preempt the next piece, which is applying variables to this as well. You can't really talk about radicals in both at the same time if you're not prepared to talk about both at the same time. So we're going to split it into two, and we'll do the radical portion next time as well. So let's go ahead and get started. Okay, first couple things to note. In case you're unaware, a radical is any statement inside of a square root. So for example, if I have the radical of 72. Now, a few details about any radical. When it comes to a radical, there are certain components that are named and certain components that are talked about. So for example, this symbol is referred to as the radical. The symbol is radical. The number is referred to as the radicand. R-A-D-I-C-A-N-D, radicand. And the entire thing is talked about as the radical expression. Now, a radical expression is both the radical and the radicand combined. And the radical expression refers to not just this, but the simplified version as well. So for this particular problem, the simplified version would be something like 6 square root 2. And so in this case, this radical expression and this radical expression are the same despite having different radicands, and this one having a coefficient. And so in this case, I need to note that this is how we will identify all of our terms. Next thing to note that if there is a number out front, this is of course referred to as a coefficient. And that 6 radical 2 means 6 times the radical of 2. And because of that multiplication property, it means that these two expressions are equivalent. Square root of 2 times 6. Remember, that's our commutative property. We can switch around the order if we need to. And so, because it's just multiplication, the order isn't important, but we again agree that the number should come first and the radical should come second, because that's how we do it in math, is we have agreed upon ways of writing everything. Now, it should be noted that if I take a basic square root, like the square root of 25, which we should all know, a square root of 25 is typically listed as 5, but it's important to note that when you take a square root, there should be two solutions, the positive solution and the negative solution. Now, the positive solution has a fancy name. That fancy name is referred to as, the positive solution is referred to as the principal square root. There we go. And so, if you see the square root of 25, it is common to just write 5 because it is the principal. It is the main root. In this case, I spelled that wrong. Principal, L-E, principal square root. Principal means it's your, person above you. So the principal square root is one which is the main one. It's the one where you have the radicand and the positive result. Yes, it is true that the other exists, but we will concern most of our solutions tonight with just looking at the principal square root. Because otherwise, if you don't put a plus or minus, it's wrong, and that's annoying. So for tonight, we're going to primarily focus our answers on the principal square root. Know that the other solution does exist. So for tonight, if you see a homework question that asks what the square root of 36, it is fine to write just 6, because that is the principal square root. You should either write 6 or plus or minus 6 in your homework. But you should not write the negative solution. The negative solution is not the principal. Now, that's a big detail that is oftentimes missed, because either people just write 6 and forget that there's a second option, or they write the plus or minus and forget the 6 is the important one. And so make sure you know that there are two solutions, but you are consciously choosing the one that is positive because it is the principal. Now, next. Anytime we talk about roots, there's some properties to note about roots. First of all, there is the cancellation property. The cancellation property states that the square root may be cancelled by something that is squared. So, the square and the square root may cancel. Now, this is not the only way of writing this statement. It is equivalent to writing the square root of a squared. Squares and square roots cancel whether they are inside or outside. Notice that I did not put plus or minus a right now. Even though I know it should have two solutions, I'm just writing the principal solution of a. So, the square root and the square end up canceling. The square root and the square end up canceling. Notice that it's only with a on the inside that this works. If I have something else, like say for example, it does not apply here. If I have like the square root of a squared b, you can't just cancel the square and the square root and get ab. That doesn't work. There has to be a square either applied to the entire thing or outside of the entire thing in order for them to cancel. So, this is one that is a common mistake, is that they try to cancel pieces of the square root. Now, there is another property that's helpful here. It is called the product rule of radicals. The product rule of radicals states that for any radical which has two terms inside of it, let's call them a and b, you may choose to rewrite them as the product of two separate radicals. So I can choose to write one radical as two radicals, as long as they are separated by multiplication in both cases. Or I can choose to write, two radicals as one radical, because it works both ways. And so we'll use our symbols. This relationship works in both directions. There's also one that states there is a quotient rule. It works much the same way. If I have like the square root of a over b, it may be rewritten as the square root of a divided by the square root of b. In other words, radicals can be split or connected as long as it's multiplication and division. Now, ways this does not work. I feel like I should do this more often because I think it's really helpful. The square root of a plus b does not equal square root of a plus square root of b. This doesn't work. This is not true. Try this with any number, okay? Pick like, what's some good examples here? 9 and 16. So like if I choose the number a to be 9, number b to be 16, this statement is simply not true. Because 9 plus 16 would be 25, and square root of 9 would be 3, square root of 16 would be 4, but we all know the square root of 25 is 5. And 5 does not equal 3 plus 4. And so you cannot split these if there's addition involved. And the same goes for subtraction. You cannot split if there's addition or subtraction. You can only split if there's multiplication or if there's division. And you cannot join if there's addition or subtraction. You can only join if there's multiplication or division. So let's talk about like where most people get their problems in mathematics. at least in radicals, and it comes from simplifying radicals. So let's look at some ones that we'll talk about how to simplify a radical. Now, when you simplify a radical, one of a couple things can happen. Either, when you simplify them, they can cause the radicals to disappear, or you can cause the radicals to break down, meaning that the radicand reduces in value. So when you simplify, there are two main goals. One, you either want the radical to disappear using the cancellation property, or two, you want the radicand to be as small as possible. You want that radicand small. Okay, let's look at one that you may have seen before if you've taken a class in using radicals. Square root of 98. Now, there are a bunch of different methods people use in order to simplify this. I want to showcase a couple. I love showing different options on how to approach a problem because I think it's really useful and helpful to see it that way. So let's talk about how to simplify the square root of 98. Now, my goal, remember, is either to make the radical disappear, use the cancellation property, or to make the radicand as small as possible. So, one of the ways to do this is called the factorization method. What that means is we're going to take that square root of 98 and we're going to break it down into factors. So the square root of 98 can be broken down into the following set of numbers. So 98 can be broken down into 2 times 7 times 7. This is a common thing to do. And in fact, some people even use something called a factor tree to do this. They would say 98 breaks down into 2 and 49. 49 breaks down into 7 and 7. And then these three pieces at the end of our factor tree end up going inside the radical. Now, why would you factor it this way? Why would you take 98 and break it down? We haven't changed anything because 2 times 7 is 98, so nothing's different. My radical hasn't disappeared, and I haven't reduced my radicand. So why would I do this? Well, what you can do now is write this as the square root of 2 times 7 squared. Remember from 2 times ago, if you have two things being multiplied together, you can always write them as being squared. So 7 times 7 is equivalent to 7 squared. Now I can use my property, which allows me to split this into two components. Because they're being multiplied, we can break it down into two radicals. And as you might remember, the square and the square root end up canceling, because they're the only things in there, leaving us with square root of 2 times 7, or 7 square root 2. This method works great. Notice how it uses properties to do it, and these properties are all valid properties, and how it meets the end criteria of one of these two options needs to happen. Now, the radical didn't disappear, right? There's still a radical in the problem. But what did happen is the radicand, the number inside the radical, has reduced. Instead of being a 98 in the radical, it is now a 2 in the radical. And so we'd say this is a simpler solution. Now, next component to note. So this is, one option. Now, a secondary option that is very, very similar is to also factor and then use the factors to end up canceling. Now, so once again, we look at the square root of 98, the square root of 98. Now, what you're going to do is you want to look at specific factors that are squares. So instead of breaking 98 down into 2, 7, and 7, we break 98 down into 2 and 49. Then we use the exact same property as before, where we split it into 2 And then we know the square root of 49 is a number. Square root of 49 is 7, so this becomes 2 times 7, which is 7 square root of 2. We end up with the exact same solution, but it's just a different way of looking at it. In this case, I am trying to target a specific factor that we know is going to cancel down the road. Now, this top one, I refer to this top one as the grunt method. It's brute force. You take the 98, you break it as far down as you can, and then go back and try to fix it. This method, I like to think of it as the subtle method. You don't know where the subtle means quiet, it means sleek, it means efficient, right? You describe a sporty car as having a subtle look. You describe a pickup as being like a grunt, because it's, it's meant to do work, whereas this one's meant to look nice. Okay? Notice that in doing it this way, we cut out a couple of steps that end up doing the same thing, right? Instead of breaking it into 7 times 7, we just look at it as 7 squared, which is 49, and then we cancel the 49 with the square root to get 7. It cuts out a couple of middle steps here. It's more subtle. But again, it takes a little bit of more extra practice because you have to know your perfect squares. And so one of the things that I tell people that if you want to do radicals better, one of the best things I can tell you is memorize perfect squares. When I was in elementary, we had a teacher that was really big into math. She loved it. She loved teaching it. And one of the things she made us do, we had to memorize the full table of squares from 1 to 25. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. You memorize them all the way up until you get to 25 squared, which is 625. And then that can really help do some of these radicals because you look at this and go, oh, I know that 98 breaks down into 49. And that's one of my perfect squares. And it makes it a little faster and easier to do if you're willing to take a look at it. If you're not, then it's not so great. Kind of just gets in your way. Now, it is important to note, when you have a problem like this, that any operations that are inside the radical should be done first. So if I write a statement like the square root of, let's say 25 plus 144. According to order of operations, I should do the inside math first, because remember, inside of a radical is a secret set of parentheses. These are in parentheses, and parentheses should always come first, meaning I should take the time to simplify this as the square root of 169 before bothering to try to break this down, which it breaks down into 13 squared, or 13. Similarly, if there's even more extreme substances inside of the radical, those should be done first. For example, if I wrote a statement like the square root of another square root, as you'll see one in your homework. If I wrote the square root of 81, well, I have to do the inner square root first, and the square root of 81 is 9, and then I have to do the outer square root second, which would be 3. If there is operations that are outside the radical, like say the square root of 49 minus the square root of 64, then I cannot use any rules to combine these together. I need to simplify the left radical and the right radical separately, because a radical is a form of power. It's a form of exponent, as we'll talk about more later. The square root of 49 is 7. The square root of 64 is 8. And then I can take the subtraction. Remember, you have to do parentheses followed by exponents. Inside of these radicals is 49, there's nothing to simplify. Inside of this radical is 64, there's nothing to simplify. But the square root of 49 can be simplified, and should be done next, because it's an exponent. The square root of 64 should come next, because it's an exponent. I should do subtraction last, because subtraction always goes last. So, this is a common refrain when it comes to these kinds of problems. How do we actually fix what's going on? But let's look at some that are a little less interesting, shall we? So we'll follow these same basic rules the entire time. Our goal is either to make the radical disappear, which is primary goal number 1, or secondary goal, our goal is to reduce the radicand. If possible, reducing the radicand is a good option. So let's look at our next one. Square root of 300. Now, one way of doing this is to take this function, just like we did before. We could do the entire factorization, which means we take 300 and try to break it down into as many different pieces as possible. So I can see right there that 300 breaks down into 30 times 10. 10 breaks down into 2 and 5. This is called a prime factorization using a factor tree. 30 breaks down into 6 and 5. 6 breaks down into 2 and 3. And so now we can take all these little bubbles at the end of our tree and we can write them out. We have 2, 3, 2, 2, 3, 5, 2, and 5. This is one method. Now, from here, I remember that I can reorder anything that I wish, as long as they're all being multiplied. So I could, for example, move the 2's to become together, and move the 5's to come together, allowing me to rewrite them using exponents. This becomes 2 squared times 3 times 5 squared. Then we can use our product rule to split this into, instead of the product rule can be applied as many times as you want. So if there's 3 things inside, you could break it into 3 radicals. From here, it's clear the 2 and the square root, or the square root and the power of 2 are going to cancel, leaving a 2 behind. There's nothing to cancel with the 3, so it just stays a 3. And then the 5 will have the 2 square root cancel, leaving us with a 5. And then we have to simplify anything we can. This becomes 2 times 5 times the square root of 3, or 10 square root of 3. Like I said, this is called the grunt method. You work, it's very tedious. You have to find all these little pieces and make them work. It's a pain. Let's compare this to the other method now. So like I said, this is that grunt method, where you utilize the entire factor tree and then take all the pieces and put them into pairs and break them out as we go. This method is fine, but it's tedious. It takes time. Alternatively, we could have just broken this down into 3 times 100. Because 3 times 100 is also 300. 2 times 3 times 5 times 2 times 5 is 300, but so is 3 times 100. And this one is much better, because the square root of 100 is already known to be 10. Meaning I end up with 10 square root of 3. This one's much more subtle. It requires more practice. It requires more understanding. It requires seeing the 100 rather than seeing it as a collection of different terms. Now, in the end, they both get the same result. The difficulty is, with this one especially, if you don't spot the 100, this is hard to do. Because, like, look what we did first. I broke this down into 30 and 10, neither of which have good factors. And so because of that, I had to keep going and breaking down even farther to get to all my pieces so I could actually solve this problem. But it worked. Like, if I break it down my first time and I don't get nice numbers like 100 or any of those other perfect squares, then one of the things I can do is break it down all the way. Now, alternatively, you could break it down partially. This is kind of like the mix. You could break it down 300 one more time into, let's say, 25 times 12. 25 times 12 is 300. But here's the thing. If I break this down, between the square root of 25 times the square root of 12, this will become 5 times the square root of 12. The issue with this is that our goal is to get it to be the smallest, right? The smallest possible value. It turns out 12 can be reduced. It can be brought lower, because 12 can be broken down into 4 and 3. And because it can be broken down into 4 and 3, we can break that down into 5 times the square root of 4 times the square root of 3, which becomes 5 times 2 times the square root of 3, which leads us right back into 10 square root of 3. Remember, the goal is that we all agree this is the answer. And so while this is technically true, this is the right answer, because it's the smallest radicand. This is a true statement. If you type in 5 times the square root of 12 into a calculator, and then type in the square root of 30, or sorry, the square root of 300, or you type in 10 square root of 3, all three of these are the same decimal. But this one is the agreed upon simplified solution because it matches our two properties, right? Either the radical needs to disappear, or the radicand needs to be as small as possible. That's how we define being simplified. And in this case, that's how we do it. Let's look at another. Let's look at something like the square root of 216 over 12. Now, with a problem like this, there are a couple ways to approach it. Because it's inside the radical, we could, as a first option, we could take 216 and divide it by 12. And get a number. As it turns out, 216 divided by 12 is a number. It's a nice round number. Alternatively, we could use the quotient rule to break it into 216 over 12. Like, both of these are fine. And both these will lead to the same solution. But that's why, if we all want to agree upon what the right solution is, there's one more piece about simplifying. When you simplify a radical, there should never be a radical in the denominator. My old instructor used to make a joke. It was, you can't run around with the radical down. And so if you look at this, the second one here, you could simplify it. It ends up becoming 6 square root 6 over 3 square root 2. Oh no, backwards. 2 square root 3. This is not acceptable. Because while yes, the top one is reduced as far as it can go, and the bottom one is reduced as far as it will go, because that radical in the denominator, you have to fix that. Now, in this example, 6 square root of 6 over 2 square root of 3, the easiest way to fix it, how we get rid of that thing in the denominator, is you need to multiply by the radical in the denominator. So if you look at this, the radical in the denominator for this problem, there's a radical 6 and a radical 3. Only one of these in the denominator. That's the radical 3. So you multiply by the radical 3. What does that do? Why does that work? How do we know this is going to make it more simple? Well, take a look. On top, we end up with 6 radical 6 times radical 3. On bottom, we end up with 2 radical 3 radical 3. Now, on bottom, we could merge these two radicals together, meaning we end up with 2 radical 3 times 3, which would be 3 squared. And on top, we could merge those two radicals together, 6 square root of 6 times 3. And then we could simplify some more. But what's going to happen is, the reason why we multiply by this specific fraction is because what happens on the bottom specifically. On the bottom, the square and the square root are going to cancel, meaning end up with just 2 times 3. On top, you can rewrite that, ending up with 6 square root of 3 squared and 2. The 6 breaks down into 2 and 3, that's why that's 3 squared. And so on bottom, we end up with just 6. On top, we end up with 6 times 3 times the square root of 2, which is, well, the 6 and the 6 can cancel, leaving 3 square root 2. That's much nicer. Much nicer to deal with. Okay? And you would get that exact same solution if you simplified it from the very beginning. But if you ever end up with a radical in the denominator, you have to take the step to get rid of that radical. It is the only solution that you can do. Now, That'll put us at a good stopping place. We'll go ahead and cut it off here for today. Make sure when you look at these problems that you simplify as far as you can. If you simplify once, that's not enough. You've got to simplify as far as it will go. So make sure you follow these 3 rules, right? The radical needs to either disappear or the radical needs to be as small as possible. But this last one is non-negotiable. You cannot have a radical in the denominator ever. It is not finished until that radical is gone. So, for your homework tonight, I will be posting those solutions or problems here in a little bit, and I'll be jumping onto a Zoom session with you guys starting at noon. Hope to see you all then. Otherwise, I'll see you guys on Monday.